Sometimes we worry too much about emerging technologies that we forget that there are powerful natural solutions as well. Say, like photosynthesis, that takes carbon dioxide and water out of the air and converts it into chemical energy. Plants, especially hardwood trees, are the superheroes of the carbon cycle. The water cycle is essential for life. The problem is when human activity gets in the way of Earth's processes that are trying to achieve a balance for a livable planet, maybe we should try to help the Earth instead of fighting against it.
I totally agree. In our Getting Back to Nature episode, we had the privilege to talk to Flora Moon of Expressworks on nature-based solutions to climate change, to Dr. Mahta Moghaddam, the director of the USC Viterbi Center for Arid Climate Aware, and Terry Tamminen, also from AltaSea and former head of the California EPA. We need to keep our minds open to different kinds of solutions for the energy transition, and these experts are just the ones we need to listen to.
Thank you, Dr. Mogadan, so much for being here on this episode of the Energy Transition Podcast. We're so happy to have you here.
Pleasure. Thank you.
So, Dr. Mogadan, can you tell us a little bit about your career, your current role at USC, and how you became involved as the director of USC Viterbi Center for Arid Climate Water Research?
Yeah, so I've been at USC for 12 years, and before that I was at the University of Michigan, and before that I was at the NASA Jet Propulsion Laboratory. So I would say my career evolved as a sequence of deliberate and not deliberate events. I was always very excited about science and math and engineering and physics. So for me, there was then that, my studies were going to be in that area. And so, one thing led to another. My PhD in electrical and computer engineering, did my bachelor's degree at the University of Kansas in Lawrence, Kansas, and then master's and PhD at the University of Illinois at Urbana-Champaign. And after that, I went to JPL. Now, when I did my PhD in electromagnetics, and electromagnetics is the study of electric and magnetic fields and how and all of various applications that they have. Now, I did most of my PhD work as a theoretician, so I did a lot of analysis and computations, not so much applied or hardware or measurements. But then when I went to JPL, that's when I got exposed more and more to actual system observational systems, remote sensing, satellite systems, and airborne observations using radars that were and are being used for tracking data both on Earth and for fairy bodies. So that was really the genesis of how I got interested in using engineering tools, and in particular radar systems on board airborne and spaceborne platforms to see what's happening to the Earth and the various variables that make the Earth function. And then, at JPL, I got to learn a lot about that, and I got to know and be introduced to a lot of Earth scientists, ecologists, hydrologists, people who actually run these weather and climate models, and that they use into their models, they put inputs, or they use inputs that are generated by engineers like us. Then from JPL, that was which was a fantastic experience. I was there for 12 years, and I went to University of Michigan as in my academic career, and I wanted to make that transition because I really wanted to have more contact with students, with the next generation. I wanted to be more involved in the training and coming up with more novel ideas. And at a place like JPL, it's fantastic. You could do a lot of that, but but once you go to university, then it just amplifies quite a bit. So I was very happy about that. And then I eventually came back to LA, to USC, and that has been a fantastic experience as well. So here, my group consists of several graduate students, PhD students, 9 or 10 PhD students, and postdocs. And then we have also a wonderful research faculty in the group. So, we have a whole cadre of scholars at different career stages. And also we work on a lot of projects that are related to environmental remote sensing in particular. And then you also asked me about my involvement with AWARE, which is the acronym for the center. So center was founded a few years ago through seed funding support from the Viterbi School of Engineering. AWARE and a few other centers are seed funded, and the idea for that was that the financial aspect of the seed funding wasn't as critical as just getting people together was. Basically gathering a group of colleagues and researchers who have similar research foci, and we bring them together. It's multidisciplinary. So bring people from electrical engineering, from public policy, civil engineering, computer science. So it's a multifaceted, and the focus of the center when we established it was looking at what's happening to semi-arid environments, basically ecosystems that are water constrained. Like Southern California, southwestern US, we are in a water constrained location. And we're not alone. A lot of places around the world, around the country and around the world have the same issues. And as the world's population increases, issues of fresh water and its scarcity become more and more pronounced. So we really need to understand first where water is, where is it going, what are the dynamics of water, what influences it, and how we could have a role in solving some of the problems associated with water.
Wow, that's incredible. Thank you.
I think it's pretty interesting how most of the people we talk to, they always say their career was changed through some no fault of their own, but it was never the same as what they started off doing. But well, my question for you was, when we read about the weather effects of climate change, right? Of course, we see the floods and droughts all over the news, and what different communities are impacted, and we know that weather is not the same as climate, and it is different around the world. But can research tell us a little bit about weather extremes? And I was wondering what some of the nuances of that would be.
Yeah, so first, you mentioned both weather and climate. Just to make sure that we are we have kind of at least a soft definition of both of them. We can probably say that there is what's happening to our to the environment, to the physical state of how our environment is at an almost instantaneous basis. And I say instantaneous, I don't mean just this second only, but very short term. So weather is basically the state of our surroundings on a very short scale. Climate is the longer term version of that. So if you take daily or hourly or weekly weather and you form some statistics of that, let's say if you average the daily temperature or you average the precipitation and you look at the standard deviation, so both the mean value and the variability around that mean over a much longer period of time, that then becomes climate. And climate is usually defined not even on an annual basis, but maybe decadal or multi-decadal basis.
How often would we? Oh, sorry.
No, go ahead. Go ahead.
How often would we see climate change sort of organically without human impact? Would you think? Because you say it's defined on a decade-long basis, so would it alter kind of state naturally, or I'm not?
Yeah, I mean, people talk about decadal, multi-decadal, like millennial type variations in climate. So we talked about the climate in the last century versus what's going to happen a century from now. So it needs a lot of bridging, a lot of the slower signals, the slower response that defines climate. And so I think you also asked the question of how does human activity figure in? Was that part of your question?
Yeah, I know. My question was like, how would the climate change without human activity? But then how also, I mean, yeah, I guess that naturally goes.
Right. Yeah. So yeah, I mean, the climate has changed over millions and millions of years. I mean, we can start from literally when the Earth started cooling, as the saying goes, and work it through the various epochs and eras. So for sure, things have been changing. And even if there were no humans, there were no human activity, more likely than not, things would change yet again. So that part, I think that there's, from a scientific perspective, there's definitely agreement on that, that there is some innate variability having to do with climate, regardless of human activity. But I guess what we hear more recently in terms of climate change, the important thing about that is how has the presence of the human race and our activities that actually accelerated or impacted climate change. I don't think anyone from the scientific perspective would say that there wouldn't be climate change without humans. But the point here is that the activities of humans have accelerated or impacted such change.
Well, what kind of factors impact a climate, and why does it vary around the world? Like, what kind of would it be mainly geological, or like what would be the factors that contribute towards that?
So a lot of the so first I will give you a disclaimer that by training I'm not a climate scientist, and we don't do climate models, so I learn a lot from my colleagues who are climate scientists and ecosystem modelers. So I address your question from the perspective of water and energy. So in terms of how climate might change and how the signature of energy and water might look like. So imagine you have a body of water, say the ocean or the lake. Sun is incident on it, the energy is incident on it. The energy causes the water to evaporate, go up in off clouds. At some point, of course, the clouds will round, they form, and at some point they could cause precipitation. And the precipitation comes down on Earth, depending on where it's coming down, it will move and redistribute itself. And it would, some of it will fall down a hill, some of it will go through the Earth. Maybe it could eventually figure into groundwater resources. Some of it would run on the ocean. Some of it we capture and drink, so there's all kinds of things that happen, and the water redistributes and gets partitioned to different pieces. Plants, of course, absorb water and they go through photosynthesis using the energy of the sun again. So there's this whole cycle that is innate in the earth. So it's basically the marriage of energy and water is very fundamental. The movement of water is determined by energy, or it's driven by energy, and the redistribution of energy to a large extent also depends on how water gets redistributed. So they definitely always go hand in hand. And then of course there's carbon, the carbon cycle, which is also very much interconnected with water and energy. For example, if you think of plants, which have a lot of carbon, they do photosynthesis, they sequester carbon, and then so that they need energy and they need water. So it's a very harmonious coexistence and codependence of all of these cycles together. Now, the way that in which that any of these could change or could be disturbed is, for example, if we somehow change the energy part of the equation in here. Let's say that, okay, the sun is going to be in for as far as our human life is concerned, it's an infinite source of energy, right? I mean, it's going to go on for millions of years, probably. So that's an infinite source of incoming energy. But if somehow we change, for example, the atmosphere, if the balance of the constituents of the atmospheric gases gets disturbed or changed, then that's how we change the incident energy on the Earth's ecosystems. And as a result of that, partially as a result of that, then the cycling of water will change as well. So for example, if we have inordinate amount of greenhouse gases going into the atmosphere, and they would cause the incident, again, the incident radiation comes in to get trapped more than if we didn't have such greenhouse gases, then then the balance would be different and the precipitation would be different. Some of the reasons that we are seeing, but these are scientific hypotheses and proven for the most part hypotheses and theories, that, because now the greenhouse gases are intensifying, that you're trapping heat, and that's the extremes of weather, especially weather events, the adverse events.
Yeah.
And by the way, I should mention that when we talk about greenhouse gases, I think the first thing people think about is carbon dioxide, which is true. Of course, methane is there too as a very potent gas. But the interesting thing is that actually water vapor is the most prominent greenhouse gas. So
Really?
there's much more water vapor in the atmosphere than there's carbon dioxide. And it's something that we don't really talk about or think about too much, partially because water doesn't really stay, that the same water molecule doesn't stay up there for a very long time. So the so-called resident time, water vapor is very short, whereas the other ones, especially CO2 and methane, they have a much longer residence time. So their effects just tend to get amplified.
Yeah. Okay, thank you.
And you explained the relationship of how, the water and energy systems interact. But with systems like hydroelectric plants being one system where they interact, are there any other relationships that we should pay attention to?
So that's a really interesting topic. Of course, the way the hydroelectric dam works, for example, is that you have stored a lot of water at probably high elevation, and you open part of the dam, water flows, the energy of its flow turns some kind of turbine blades, and that mechanical movement, you capture it into electric energy. And then the question is, okay, how are you going to replenish? Where's the next water going to come from, right? Because the premise of the operation of this hydroelectric dam is that, you have water that you can release. So you can't, it's not an indefinite thing unless you can replenish it. And that's how, we go back again to, okay, how much precipitation am I getting? When is it going to come? Is it going to be enough? Is it going to be too much that it's going to overflow? So a lot of these climate events eventually also find impact or find a presence in other aspects of the connection between energy and water. But yeah, that's a pretty interesting observation, interesting topic that you brought up. And the other thing that I briefly mentioned also is photosynthesis, because also real energy of sun, so that they can extract water and other nutrients, and through their make carbon-based mass, which becomes food for the rest of us. So that's another it's a very intimate relationship between water, energy, and carbon in the food that we eat.
Yeah, and you mentioned, having that, it seems like there needs to be that balance, with water and with just emerging like technology uses like these plants, right? So a lot of what we read today in energy transition is about renewable power generation and emerging technologies. Should we pay more attention to water resources?
I would say absolutely yes. Times is such an obvious issue that we tend not to even mention it, because we think, oh, it's so obvious. Someone must be doing something about it. But in fact, that's not true. Our water resources are limited. The fresh water is a scarce resource on Earth. Of course, we're called the blue planet or the water planet because like 70 or 75% of Earth is water, but it's the oceans. So that's not fresh water. It's not suitable for human use. And then the other interesting set of facts to keep in mind is that of that limited amount of fresh water that we have, most of it actually is locked in glaciers and ice sheets. Of course, it's a good thing because they tend to regulate the energy cycle and the overall temperature of the Earth. But as you've I'm sure heard and have read about, our average global temperature is rising, And it's kind of a vicious cycle because that's causing the glaciers also to melt. And then when that supply of fresh water melts, it's going to the oceans. So by some accounts, you could argue that we're actually losing a total amount of fresh water because the ice caps, as they melt, they're going to join salt water. And then the other thing is that there's also a very large supply of groundwater under the surface. And it could be shallow groundwater in California. If you go up in the Mojave Desert, there are some shallow aquifers. And then there's also some very deep ones throughout the country, definitely in California, but also in the Midwest, and everywhere. There's a lot of groundwater. The issue with groundwater is both one, even if you wanted to use all the groundwater we have, it's very hard to access. So you got to dig wells. It's just not a very scalable source of water. The other thing is that if we draw the groundwater, we're also damaging the environment. Drawing down water makes the ground surface to subside. In fact, there's a lot of evidence of that already in the California Central Valley, where there's a lot of agriculture, and because of droughts, farmers didn't have a choice but to draw groundwater. And I'll talk about it when I said they didn't have it, I'll qualify that later. But so when people are faced with a crisis and they need to use their resource, of course, they're going to go draw down water from the ground, which has had adverse effects for the environment in the form of subsidence. The problem is that once the ground subsides, you can't really push it back up. So you've forever lost that capacity to store water. And then we see that also in the Midwest. And as bad as we think the situation is in the US, it's even around the world in other areas, especially in the developing countries where the technologies aren't there to even be aware of what the problems are. Now, and then I'll include a couple of other tidbits in here, which is that, and you would say, okay, well, let's say 60-some% of water is in glaciers and ice sheets, 30-some% maybe is in groundwater. Then there's that few percent, like where is that other few percent? And the answer for that is that other few percent of fresh water is in the soil, like top layer of soil, not groundwater, not the saturated soil, the topsoil. And that we call soil moisture. And that's, for example, where the roots plant, that's actually the water that the plants use to grow and feed us. And lakes and rivers. Lakes and rivers, they don't have that much water actually compared to the other stores of water, even though we see them and they're the more visible part of fresh water, but the actual quantity is not as much. And of course, they easily get impacted by the warming climate and the drier weather patterns. So I can keep talking about groundwater, but I don't want to interrupt your questioning. I was going to talk about how, when I said earlier, how the farmers may not have a choice for drawing down groundwater. I can.
Yeah, please, as much as you would like to explain, we would love to hear it.
Okay. Yeah, so now we get into a little bit of the thought about technologies and how, as engineers and technologists and scientists, we can roll and understand, well, not just to understand, but also come up with solutions. So I mentioned earlier that during droughts, farmers tend to just use groundwater because there's not enough precipitation, but they just need to survive. I mean, it's a matter of their livelihood. They need to produce, and the rest of us need the food. Like California has a huge role in feeding the country, and we just can't say, okay, it's a drought, we're not going to grow for that. It's just not sustainable. So they draw down water. The problem is that as they draw down water, many farmers, to the best of my knowledge, they don't have a good way of knowing when there's enough water available already. So a lot of them tend to overwater the plants. And overwatering harms. One is that we wasted a precious resource, water. The second thing is that there's a lot of chemicals that are used in the farming industry. And when you overwater, those chemicals tend to get washed down. They go down, they permeate the layers, and they go back to whatever ground resource or groundwater is left, and they actually contaminate the supplies of groundwater and soil. So there's kind of this double whammy effect for not having good control over irrigation is enough irrigation. So that's one way in which that technologies can work. To know a couple of things. First, you need to know how much water has already been given to the plant. So you have a near real-time way of monitoring how much soil moisture is available to your plants. Let's say if you're a farmer, you need to know if your field has had enough, but then you need to act quick. Once you know that you have enough water, just stop right there, as opposed to keep irrigating just to be on the safe side. It's unnecessary. I mean, once the plant has enough water, it has enough water, right? It's safe. So there's no need to just, hedge your bets by giving it more water. And just a small thing like that is going to save a lot of water. And ultimately, besides the longer term benefits of not drawing down too much groundwater, it has also short-term benefit for the farmers in the sense that they would use less energy. Here we're back in the energy topic. Use less energy to pump the water up from the well, because if you want to get the water out, it's the opposite of pushing water down, which releases energy. But when you want to bring it up, you have to spend energy to bring it up. And there's a huge electric bill, actually, that's with pumping up water. So there will be multiple benefits for regulated. I don't mean like regulation type of regulating. I mean in the sense that at the farmer or a field level to have control over how much water you are providing to the plants, enough for productivity, but not too much to cause other damage.
Wow, yeah, you bring up a lot of great points on, just again finding that balance with water usage in general. Thank you.
Of course, yeah.
And so according to the website, the purpose of the AWARE research program is to address the severe deficiencies in monitoring and understanding water scarcity in arid climates. And I was wondering what your key insights of your research were to date, till now.
So there is a lot that is taking place currently here at USC in our with our group of colleagues, and also with a lot of our collaborators outside of USC, including government agencies. So it's a kind of a multi-tiered approach. First, we need to quantify the extent of the problem. We need to understand and characterize where water is, how it's distributed, where is it, and for how long. And then we could think about water resources somewhat in terms of what I mentioned earlier, which is that we have the glaciers and ice caps. So our group, we're not really studying those, because we're focusing more on the arid and semi-arid dry environments. So if you put those aside, then we're talking about soil moisture, and we're talking about surface water, rivers and lakes, and also groundwater. There is a scarcity of information, it turns out, about especially groundwater. I would also say that about snow, even though, I mean, I do think of California, which is generally a dry place, as also the OE place, because we have the sea, we do collect snow, but overall, on balance, we're living in a kind of a drier state environment, the whole southwestern US. So I would add snow to one of the quantities that really know much about. Measuring snow is very easy. You could just walk it and have a stick and see how much, how deep the snow is, or you could melt it and see how much water content it has. However, on a large scale, when you're looking at let's say, the whole Sierras or even a given hillside. It's really not easy to do that because it's not practical to walk the whole place and measure things, especially if you want measurements every day because you want to see how things are changing.
Yeah.
So we don't really have right now we are deficient in the tool for high resolution and fast observations of a lot of our water resources, in particular groundwater and snow. Soil moisture also is very important because not only it feeds us, it feeds the plants and therefore it feeds us, but also it regulates that energy exchange between the earth and the atmosphere. It's this boundary layer that has a big say in how much is evaporated versus how much water stays. So we need to know soil moisture. There are satellite sources of soil moisture. So NASA has a very well-known mission called the Soil Moisture Active Passive mission. It provides soil moisture information globally on a 2 or 3 day basis. But not only it's not every day, so it's only 2 or 3 days, but also it has a very coarse resolution. We're talking about at best 9 kilometers. Oftentimes, the more reliable products could be at like 36 kilometer. So we don't have fine resolution crop level soil moisture information. So that's also, I would put that also in a kind of deficient information category. So yeah, to make an impact. So going back to your question about what the center and our group of faculty are concerned with, first order of business is to generate information about the quantity and the dynamics of water resources, in particular soil moisture, snow, and groundwater. The second thing, once we achieve that, and the community is far from completely having achieved that. So it's a research topic. It's something that we continue to work on. But we have developed some methods, and I'll be happy to talk to you about that as well. But let's say if we solve that problem, let's say that now we have all kinds of data that we want, very fast, high resolution, then what? The next step after having that information is that how we collaborate, how we interact with the actual climate scientists, the hydrologists, the ecologists, the weather and forecasters, to provide this information to them so that they can run their models reliably, more accurately, and give us better projections of what we expect in the short term and in the long term. So that's the second step. And then let's say we did that too, and we came up with very accurate forecasts, then what? So after that, it's okay, what do we do about it? What are the solutions that we come up with? And that's a whole new area, and that's a very vast topic. And that's when we have to, as scientists and engineers, we have to lend our tools to the public agencies, to the public, and to come up with solutions that are first technical perspective feasible. They're also affordable and scalable. So, for example, people talk about, I'm going to digress just a little bit in terms of solutions. When people talk about electrification, electric cars, great, yes, I mean, a car would emit less fossil fuels if it's electric, but is that a scalable solution? Can the disadvantaged communities have access to electric cars? The answer may be no. Maybe one day with better, newer technologies, the answer will be yes. But that's about having solutions which ultimately are scalable and affordable.
Mm-hmm. Well, when we're talking about these arid climates, people have lived in arid climates for generations, and different populations have adapted to arid climates in different ways, right? And so how many populations, or what is your estimate of people who would be affected by these arid climates that are now emerging, and what technologies would be helping them adapt to that change?
Yeah, I mean, you're right that human race has adapted over and over again. And then, we talk about sustainability in that sense. So I think your question definitely leads into the question of sustainability. And what do we mean? Do we just want to get by, or do we want to flourish?
Yeah.
Right. We could get by. You could say, okay, well, forget I don't want a yard, which is, I mean, I'm going to exaggerate just a little bit here. It's like, okay, I don't want a yard. I won't water anything. Everything will go yellow. It's fine. I won't swim, not just in my swimming pool, but not a lake or a river again, because if they dry down, okay, I won't do it. I could say, okay, well, there's not enough energy, for example. Let's say if the hydroelectric dam doesn't work and I don't have energy to be on Zoom with you or to use my phone. So, okay, well, I'll just use it less. But do we really want to do that? I mean, do we really compromise? And maybe compromise is not the right word. Of course, we have to make some compromises. But the question is that we don't really want to, we don't want to reduce the quality of our lives. We want to flourish as a population. We want to do better things. We want to do more things. We want to have higher tech stuff. Yeah, sure. I want to have, all kinds of personal communication devices. I want to be in touch with you. I want to be able to collaborate on my shared like Google Doc or Teams, these shared resources, which are very energy intensive, by the way. When you document, some server is running a lot in the background. So it's the kind of stuff like that we give up. We just want to get better. And that's maybe where I would make a distinction between what the human race has had to do to adapt generation after generation versus to actually flourish. So in the face of change, one is, what do we do to minimize the impacts of change or even reduce the adverse change? And then at some point, how do we not just mitigate, but adapt in the sense of making advancements, right? For example, how do I make my electronics more efficient? How do I make my phone, instead of having to charge it with the same amount of usage, instead of charging it once a day, can I charge it once a week and have it still do the same amount of work? And that's the kind of research that we would like to engage in. Also, information is critical, so it's always good to continue to be able to quantify the current state so that we put check marks into our design and evaluation process. We don't go open loop. So we still want to know how much water there is, how much energy there is, and what should be our goal for consumption.
Yeah, absolutely. And are there any technologies in particular you guys are focusing on that would help people's quality of life?
Right. Yeah. So I'll talk about what we're doing, like in my group and within some of the researchers in AWARE. So I'll give you a little bit more of a synopsis of what else is going on in the Viterbi school. So what we're doing now, we're focusing, among other things, on quantifying water resources. So more recently, we have developed technologies on UAVs or drones. So these are miniaturized radar systems that we could put on these drones, and the drones can fly on demand whenever you want it. And then they could produce very high resolution information about snow properties, about the state of subsurface soil, so soil moisture profiles. We have shown it's a kind of a limited demonstration, but we are expanding on that, that we can also use this radar on drone technology to look at groundwater resources. So it's a kind of an inexpensive technology. After we're done developing, a lot of the development costs, of course, are high to most people. But once you do that, the actual system is going to be pretty low cost. So any farmer can have one of these things, or they can actually have a swarm of these drones flying and mapping their field on a daily basis to tell them how much soil moisture there is. Did I irrigate enough? Or do I turn on the water now? Or how much of the groundwater have I used? Have things changed? Or does the hillside have enough snow to feed me for the summertime?
Yeah.
So that's one of the things I'm working on. And we've worked also with government agencies, especially NASA and USGS, US Geological Survey, on developing technologies. And some of the work that I mentioned with our drones was actually started by both USGS and NASA. With NASA, we collaborate a lot on satellite sources of information. We take the data from NASA satellites, and then we can convert them into products that the scientists, modelers, or other users of those products can get their hands on. Now, in terms of, so that's a lot of the work going on in my own group. But within Viterbi, there's also a lot of other work that goes on. I'll give you one example. Well, I'll give you two examples. One is related to what I mentioned earlier, to let's make our electronics more efficient. So we have faculty in Viterbi who are working exactly on that, looking to reduce the energy consumption of the little semiconductor devices, the chips that go into our personal communication devices, and they're trying to reduce consumption. I mean, even if you can reduce the consumption of your generic chip by 20%, that's a huge saving in energy. So that's big. And then hopefully, we could do even, maybe we could do order of magnitude reduction of that. And I think it's feasible. It may not be tomorrow or next year, but it would be 5 or 10 years from now. I think there's a lot of opportunity for that. Thing that's happening actually in Viterbi that's pretty exciting is there's a new center called Rewater, and Professor Amy Childress runs that center. It's a center that is being supported by the Army Corps of Engineers. And the purpose of that center is to basically recycle water. So it's reusable or it's reusing water into potable water. A lot of people just cringe when they say, okay, well, I will reuse the water. I think there's nothing to cringe about, because it's based on scientific principles. You recycle water and it's as good as new, even better. It's like pure water. And the trick there is how to do it, again, in an energy efficient way. Right. So what are the techniques, what are the technologies we need to develop to achieve that? Do it energy efficiently, but also make sure water doesn't go to waste. No pun intended.
Yes. I guess the main issue would also be like, people's inherent biases and stuff towards those kind of things, or people's reaction, or getting public adoption of it, not just having, the proof of concept.
You are absolutely right. That is oftentimes a huge barrier. In that, I mean, water is a great reuse of water is a great example, and just expecting people to behavior that they've been used to for years and years is really, really difficult. So there's, I think there's a lot of work that falls on us as technologists to be able to communicate that to people. That look, these are based on sound principles, and just I mean, you don't want to tell people just to trust me. You can't just say that. You gotta explain. You gotta explain in a way that is accessible to the general population.
Yeah, you bring up a lot of wonderful points. As you mentioned before, with the technology that your research is doing with drones, right? Within the AWARE program, there's a lot of interest in investigating, the relationship between energy, water, and land use management practices, especially in water scarce environments, with methods of using these remote sensing applications. Could you further expand on what the program is researching and what you are researching, if there was including the drones itself?
Right, sure. So we are currently working with U.S. Geological Survey and NASA on how we can make these drones produce the kind of products that are usable for end applications. So with the USGS, we're working with them under a program they have. It's called the Next Generation Water Observing System, or NGWOS. And we are collaborating on multiple aspects. One is quantifying snow. a lot of our water resources do come from snow. So the winter and spring snow has a huge impact on water is going to be available. I mean, Southern California in general, we're very much dependent on that. I would say nationwide. I mean, Colorado for sure. We're dependent on that. And if you look at a lot of the major river basins in the country, most of the major rivers are fed from snowpack. So we're working with GS to develop these techniques to quantify snowpack and also to quantify what is called the snow water equivalent, SWE, SWE, snow water equivalent. Snow water equivalent basically is how much water there is in a given volume of snow, because not all snow is the same. I mean, you have no powdery, you have really watery snow. Higher SWE, snow water equivalent, it just means you have more water. So you don't want to just know the depth snow, but you also want to know how much water there is in that snow, which kind of feeds into the water resources. So we are working with them on that. And we're also working with them on quantifying how much water the rivers. So river bathymetry, that's a technical term. River bathymetry is of great interest to the USGS. It's of great interest to the nation because we need to know how much water in our rivers. That's, a very obvious source of fresh water. And it turns out it's very difficult to quantify that because you need two things to quantify how much water flows in a river. You need to know how much cross section. So if you cut the river, you need to know what that cross section is, and you need to know how fast it's flowing through that cross section. That would allow you to quantify the amount of water. There are techniques to quantify the speed with which water flows. It actually involves radars. Doppler radars can tell you how fast how the water flows. But the tougher part is knowing the river cross section. And now we're using our radar to do that. So we have developed a special version of this radar. It operates at very low frequencies, and it can actually penetrate water to several meters. And we've been able to show that with good resolution, we can map the bottom of rivers. We're still at early stage of this technology, but our current experiment has shown pretty successful. Actually, been up to the Sacramento River, and we've shown that various sections of the river.
That's incredible. Thank you.
Well, I guess that naturally flows into your role at as the head of the microwave system sensors and imaging lab, or MixHill. Could you tell us a little bit more about your work there at MixHill?
Yeah, actually, it's everything I explained. Basically, it's happening. The part of the work that is my group's work, it takes place in MixHill. It is the name of my lab, and that's where PhD students and my postdocs reside, and the wonderful research faculty as well. So there's a lot of synergy between MixHill and AWARE. Now, the AWARE Center has more faculty involved in it, and each of us have our own lab. So the name of mine is MixHill, and there are other faculty in AWARE as well.
Oh, okay. Well, thank you.
Yeah.
Dr. Moghaddam, thank you so much for your time today. It's been a real honor to have you on this podcast. But before we leave, is there anything else that we forgot to ask you that you think is important to share with our audience?
Well, thank you so much, Mila and Roshan. It's been wonderful talking to you. Wonderful questions. I really enjoyed it. And, if there's something that we should emphasize, it's something that you brought up, both of you brought up, which is how do we take the message to people? Sometimes we get so absorbed in our niche science, niche technologies that we forget that, we're doing it for a purpose. We're doing this for the betterment of humanity. And we forget to communicate that, both from kind of a high level purpose perspective and also from the technology. I mean, we really should be more proactive in being able to communicate our science, our findings, and our methods to the public. We can't expect everyone to be an expert in the area because people have different interests. We should do what we can to communicate our technologies better.
Well, thank you.
Thank you.
Well, thank you guys. Good talk to you.
You know, in Greek mythology, Gaia is the personification of Earth. The Greeks invoked Gaia in their oaths, and she should be aware if one of those broke his oath. The poets usually describe Gaia as mother of all nourishing and all productive, who must be honored. And there are some modern science fiction writers that use Gaia as a personification of Mother Earth. The lessons from this episode should help us to better understand and appreciate nature-based solutions. After all, we live on this planet, and there is no planet B.
That's a really interesting way to think about all this. If we can better understand natural processes like the carbon cycle and the water cycle and help it along a little bit, we'll have a very powerful ally in the energy transition.
Thank you so much for joining us for the future of energy. Special thanks to each of our guests today and to our technical wizard, Abhi, for his important contributions to this episode. Don't forget to subscribe to our podcast so you can automatically get access to all our new episodes. You can find us on Apple, Spotify, YouTube, or wherever you get your podcasts.